All right, ladies and gentlemen, class recording has started. So yesterday, we talked about our first type of motion graph, and that was a position versus time graph. And in a very duh kind of way, a position time graph will answer two questions for us. What are the two questions that a position time graph will answer for us? Where something is and when it's there, right? So position and time, where and when. But then, towards the end of class yesterday, we started talking about that if we analyze that graph a little bit more, we find out that looking at the slope of the graph will actually tell us something else about that motion. What does the slope on a position versus time graph tell us? Not speed, velocity. Okay? Because we'll see in a second that, well, first, do we understand the difference between speed and velocity? There's basically one thing, direction, right? But we'll see that the slopes can be positive and slopes can be negative, and that's going to tell us about how an object is moving, which way it's moving, and all that fun stuff. Okay? Good with that quick intro? Okay. Most of the second page of the slides that I gave to you is analyzing a couple of different position versus time graphs. So let's start off with a pretty simple one that looks just like this. Okay? Why don't we take 30 seconds, talk to the person next to you, and come up with a description of the motion of this object based off of this position versus time graph. Remember, I think we talked about this yesterday. Like here, it says distance, but let's say that that's position. All right, 30 seconds. Talk to the person next to you. Describe the motion of this object. Go. That's just a sloppy ellipse. All right. So before we discuss, would anybody like to be brave and come up here to the front of the room and physically demonstrate the motion on this graph for us in front here? So, no, I give them a lot. So, Edie, do you want to do that? Yeah. Okay. Before you do that, Edie, let's set it. So, if we're going to do this, right? We have to set something up for Edie first, right? What do we have to tell him? Reference point, right? Edie, let's call this the reference point. This post right here. We'll call this the reference point. Okay. What else do we need to tell him? Direction system, right? So why don't we call it that way positive, this way negative. Okay. So I will give you a countdown. 3, 2, 1, go. And when I say go, that will be like time 0 on this graph. Okay? Are we ready?
Yes.
Are you sure you're ready? Okay. Right. Should we wait to critique him until afterwards, or should we critique him right now? What?
Not standing right.
All right, Edie. 3, 2, 1, go. All right. So, all right. Sorry, I asked you to be brave. I should have told you that you're going to be open to critique afterwards. All right, so he did some good things. He did some things that he could improve on, right? So, what do we want to start with? Good things or improvement? Okay, so what's one thing that he could have improved on? There's really only one thing I think that he could have improved on. Joe? And that wasn't actually what I was thinking. So
Speed up gradually.
Because there is no numbers on this graph, right?
Speed up while I'm...
No. So that's a bad thing, right? So Is what?
Say like constant speed.
Okay, so that was one thing, all right? So let's talk about this graph. Yeah, I thought you did okay. It was a fast constant speed, but it was constant. Okay? There was definitely one thing that you could improve on, though, like one definitive thing you could have improved on.
You could have counted.
I suppose so. Although there's no numbers on there, so I don't know what he would be counting. You know. Okay, he could have waited the same time at the beginning and the end, right? There's definitely one thing though that could have been improved on. What was the first thing that we had to do for him? No. What did we have to do for him first? What was the first thing we had to establish? Reference point. Edie, where did you start your graph? Does this graph start at the reference point?
No.
It doesn't, right? It starts a little bit in front of the reference point, right? So instead of starting your motion here, you probably should have started here, right? Okay. That's the one definitive thing that you probably could have done, that you could have improved on, all right? So, Edie, the pink sections that I highlighted on this graph, what do they represent?
Stand still.
Standing still. There's two ways that we can sort of justify or explain that the pink section is standing still. How do we know that the pink section is standing still? The distance or the position is staying the same, right? That's one way that we can sort of justify that. What else? The slope is equal to zero, right? Horizontal lines have zero slope. And we know that the slope is velocity, so if it's zero slope, it's zero velocity, right? All right, what about the green section? What's happening in the green section? Constant speed. Actually, fellow, we could actually go a little bit further than that. He's walking with a constant, because does the direction or does the sign of that slope change during the green section? No. So constant speed, constant direction equals constant velocity. Okay? So, as far as this graph goes, if we have any straight line on a graph, that's going to represent a constant velocity. So we actually had 3 straight lines, or I guess they were line segments if you want to talk about it that way, right? We had 3 straight line segments. 2 of them just happen to also be horizontal. And if they're horizontal, that means specifically which constant velocity are we talking about? Was the velocity constant during these pink sections? Yeah, it was just constant what? Constant 0, but it was still constant, right? So any straight line is constant velocity. Horizontal straight lines are 0 velocity, right? And on your sheet, you have spaces where you can make notes of these things right next to the pictures. Whether you fill them in or not is completely up to you, but if you want to, there's space for it. Okay? All right, good there. Okay. Graph number 2. There it is. Discuss with the person next to you. Let's do this. For our purposes right now, let's forget about the fact that that distance is in kilometers and that time is in hours. Let's just talk about it in terms of distance and time, right? Except we also said that distance isn't distance, it's position. Okay? 30 seconds. Talk. Go.
Okay.
All right.
I'll do this one.
You want to do this one?
Sure.
Same frame of reference as before. Same reference point,
Okay.
same positive direction, everything. Okay? All right, I'll give you a countdown. All right, ready? 3, 2, 1, go. All right.
That was bad.
All right, so let's critique. Okay?
Second time.
So first, okay? First, It's supposed to be an hour, yes. So. All right, first,
You want to be neutral?
pink section on this graph is representing what? Stop, no motion, right? Zero velocity. Let's do this, because we'll get into this a little bit more as we go along here today, okay? The next question I would like to discuss with the person next to you is, and this is sort of test prep as well, okay? So, the test question that I would ask you about this section is, compare and contrast the motion of the object during the green section versus the yellow section. All right? Compare and contrast the motion of the object during the green section and the yellow section. Discuss with the person next to you. Go.
The green section is going 10 miles per hour. The yellow section is going approximately 5.
Not approximately, it is 5. So I keep saying I concur.
It makes him sound smart.
Not really.
All right, so let's discuss. When I give you a compare and contrast question on a test, generally speaking, it's going to be worth 4 points. /quiz, right? When I give you a compare and contrast question, generally speaking, it's going to be worth 4 points. Okay? So let's talk about the 4 points, right? How do you get 4 points on a compare and contrast question?
Compare and contrast.
You compare and contrast,
And you explain why.
and you explain why, and you explain why. Those are your 4 points. Okay? So when we're comparing something, what does that mean?
You're showing one thing on the left.
Okay. There are 2 things that I think you could use to compare the green section and the yellow section. What is one way that green and section are similar to each other?
They're both
Okay. That's 3 things. Okay. They're both moving in the same direction. I would give you that. Okay. What else? Okay. I would give you that. They did move the same distance. Okay. That wasn't what I was thinking of. There was another one I was thinking of. They're both moving with constant velocity. Right? So any one of those 3 would be a good compare. Right? So, how do we know they're both moving in the same direction? They both have positive slope, right? And positive slope means they have positive what? They have positive velocity. And what makes positive velocities similar? If they're positive velocity, whether it's positive 6 or positive 16, they're moving in the same direction, right? So because the slope of green and yellow are both positive, we know they're moving in the same direction, right? Yes, but you said distance, right? They both move the same distance, okay? Green starts where? And ends at, and yellow starts at and ends at. So we would say that they have the same distance. We could also say something else. They also have the same displacement. Because what do we know about distance and displacement if we don't change direction? It's the same, right? Aya, they're both moving with constant velocity. How do we know that from the graph? They're both straight lines, okay? So, what would be the contrast then? What factor are we, or what description are we talking about? Shane, go ahead. Did you have your hand up or were you just stretching? Okay, sorry. You looked like you got your hand up. That's cool. So, what makes them different? Joe, I know what you're trying to say, but there's like a vocab word that would describe. The slope is different. What does the slope tell us?
Rise over rise.
Yes.
How much time it takes to go to that distance?
What is the relationship that? It's the speed, right? Okay. Does that make sense? Joe. Jason, saying that it takes a longer time to go the same distance that's what? The relationship between distance and it's slope on this graph, but that graph based on these measurements fits our definition of speed, right? How far did it go versus how long did it take to go that far, right? Yes, it is generally the slope of the graph, but on this graph in particular, because we have position on the x-axis and time on the y-axis, when we compare rise over run, that's the slope, right? Okay. All right, good there? Okay with that? All right, so on this graph, right, two things. If we have a steep slope, an object is moving with a high speed. If we have a shallow slope, it's moving with a slower speed. Okay. Notice that I used speed here, right? Okay. Not velocity. Why? We can have a steep upward slope, but we can also have a steep downward slope, right? Something that has a steep downward slope has a high speed. It's just moving which way? In the negative direction, right? A lot like this one right here. Right? What happens here? Good. Talk. Go.
Okay, it starts slow, and then it decreases speed. And yeah. It's not moving.
What?
It's not moving.
See the bottom. Oh, it's right here in front of your line. The distance stays the same, so it doesn't move.
And then it goes like that.
And then it goes.
Is it speeding up or slowing down?
Speeding up.
No.
No, that's constant speed. It's a straight line.
All life is straight.
Well, then it's a line.
It's a line. All right. So, Edie, how does this object start?
Can I demonstrate?
Sure.
Yeah.
Oh, wow.
I don't care. Make sure you get the distance right.
All right. Are you ready? Okay.
Wait,
3,
where's your
2, 1, go.
That wasn't 20 seconds.
All right.
Did you stand there for 4 hours?
That's okay.
Well, you just said it wasn't hours for me.
That's all right. Whoa, this is not a pointless argument.
Yeah, dude.
All right. So, Edie, question. I like the way that you demonstrated it because here in one dimension, we talk about backwards and forwards, right? So, question though, is the graph any different if you would have went this? Which way are you moving?
Still negative.
Still negative. Whether you're actually walking backwards or forwards doesn't totally matter, right? But which way we're going, okay? So, pink section, what's going on? No, because so our frame of reference is set up regardless of what's in that frame of reference, right? This is still the reference point, regardless of where we are in relation to that reference point, or which way we happen to be facing. Does that make sense? When you have a map of Westlake, there's the compass rose in north, south, east, and west, right? Regardless of where you are in Westlake, or which way you happen to be facing in Westlake, north is still north. Does that make sense, right? So yeah, whether we're standing here or whether we're standing here doesn't change the frame of reference that we set up to measure this motion. Does that make sense? All right, pink section. Pink section's what? No movement, right? Zero slope, position remains the same, okay? Then, right, if we look at the slope of the blue section, right, is it a constant slope? Yes, it's a constant velocity, but now it happens to be what? A negative constant velocity, right? So downward sloping lines or negatively sloping lines are objects moving in the opposite direction, or I guess we could say more generally, the what? The negative direction. Right? The negative direction is technically more descriptive, more accurate, right? All right, good there? Okay. Does anybody want to come up and do this one? Anybody? Anybody besides Edie?
I'll attempt it.
Well, you already had a chance. Does anybody really want to change? You want to do it? Come on up, Shane. So, good. All right, same frame of reference as before. Okay. All right, ready? 3, 2, 1, go. Let's talk about some good things that he did, because I don't think there was anything we really need to critique. What are some good things that Shane did in his motion? Bella, go ahead. What's one?
He started away from the reference.
Okay, so he wasn't at the reference point when he started. What's up? What else?
He didn't stop when he went back.
He didn't stop when he went backwards. He went forward and then immediately started going backwards, right? Technically, he has to stop, but that's semantics, so we won't worry about that. Okay? So someone can't go immediately from going with a positive velocity to a negative velocity. Okay? Like physically, it's impossible. So.
Do it.
No, you're still moving in the same. You just missed the whole conversation we had. So. All right. So he didn't start at the reference point. What else did he do well? When he went negative, when he went in the negative direction, he didn't go all the way back to the point that he started. Right? What else? There's one other thing I think he did that I think he did well.
His speed was constant.
His speed was constant. He went farther the second time than he stopped the first time. Good? Okay. All right. 4-point question. Compare and contrast either green section with the blue section. Compare and contrast either green section with the blue section. I will tell you this, for those of you that are going to get picky on me, okay? And it's okay, because you need information, all right? I'm not trying to trick you here, right? This graph is a general graph, all right? It doesn't have numbers on it, but I'm not trying to trick you. I'm not trying to, be picky about it. I want you to understand broad concepts, okay? So compare and contrast blue and green. Discuss. Go.
Different colors. And blue, no, green is positive direction. Green goes positive direction. Blue is negative. It's not in the same direction, but then it's become.
Same what?
Same velocity.
Not acceleration. Okay.
And a different velocity. It speeds up and it's its space goes. Green says it's increasing velocity. Blue sees decreasing velocity. Acceleration is increasing speed.
What's our definition of acceleration? What has to happen in order for there to be acceleration? Has to be a velocity has to change. Yes. So if we were measuring the acceleration of the green section, this is by the way, sorry, this is a higher level question. There wouldn't be any. Right?
Yeah, but if there was acceleration, what would that?
Hold on to that thought. We're going to talk about that in a second. Okay? All right. So, in the interest of time, here is what my answer would look like. Green and blue have the same speed, but different velocities. Okay? Why don't you guys do the explaining part? Right? Blue and green have the same speed, but a different velocity. Okay, so one's positive and one's negative. All right? but numerically looking at the slope of the line, it's the same numerically, but one's positive and one's negative, right? Does that make sense why they have the same speed but a different velocity? Yes, no, maybe? All right. Okay. Good? All right. Joe, you were jumping ahead to this, and that's okay. It's just where we go, okay? This graph. Again, I would abbreviate position with POS, but we don't want to do that. So this goes on like the internet and stuff, even though I just said it.
Nice job.
All right, now I'm going to get a parental warning, like explicit language, you know. So. All right, this graph should look familiar. This is the graph of what that you've seen recently? No, not your car. This is your marble. Okay? And Joe, this graph is what? What shape is this graph? It's a parabola. Technically, it's only half of a parabola, but it's a parabola, right? Okay. So, how... Did we get it now? They didn't get it, huh? There were a lot of people that didn't get it, so I thought I would just roll with it. So.
Well, no, but still. Slow it up.
No, I won't. Hey, this is being recorded, just so you know. So. All right, so this is the graph of your marble. How was the marble's motion different than the motion of the car? It was constantly accelerating. It was constantly, in this case, speeding up, whereas the car was constant velocity, right? Constant velocity means what about acceleration? There is none, right? Here, there is a constant acceleration. It keeps getting faster and faster and faster and faster and faster. Okay? So now, this graph doesn't have a slope. Right? We can do rise over run, but that doesn't show the graph, right? The slope of this graph actually changes. Here, it's a pretty shallow graph, right? But then, as we move along, that graph becomes steeper and steeper and steeper and steeper. What is that telling you about the motion of the object? It's going faster and faster and faster and faster. Well, Joe said the velocity or the speed. What's my answer to his question on this graph? For this graph, is there any difference? Because which way is this? It's going positive, and is it ever not going positive? No. So is there any difference between speed and velocity for this graph? No. Right. But if we had something like this, okay? So here, and this is getting into the kind of the next slide, right? Here, this graph starts off pretty shallow, right? If I draw a line next to it, that line looks like this, okay? Here, that line is steeper. Here, that line is actually less steep than it was before. What happened from blue line 1 to blue line 2? It sped up. But then what happened from blue line 2 to blue line 3? Slowed down. What happened from 3 to 4? It changed directions. By stopping and then going. You guys don't know this yet. You'll learn this, I think, when you get to pre-calc, maybe. If we were to draw these lines the whole way, at the very, very top point, the line is horizontal. Did you learn that already? I didn't know if you guys knew. Okay. Okay, my bad. So, but I think in pre-calc you start getting into like transformations of graphs, making them bigger, making them smaller, and then you look at ways they flip and stuff like that. Okay. So here at point A, right, that line would be flat. What does a flat line represent? No motion, right? Just for an instant, that object has stopped. What happened from 4 to 5? It's sped up, but it's going which way? The negative direction, right? And then finally from 5 to 6. All right, you ready for this? Okay? Here's my demonstration of the position versus time graph that I just drew. Ready? Here goes. What did the
9.8 meters a second.
its acceleration was that much? So its velocity, yeah, that was its acceleration. What's me pushing the ball upward with my hand?
Force.
Which part of the graph is me pushing the ball upward? Which number? 1. Because it's getting faster. Okay? But then from 2 to 3, what's happening to the ball on the way up? Slowing down. From 2 to 3 to A, that's the upward trip.
Does that mean it's levitating?
No. That means it momentarily stops. Okay. But then on the way back down, right, from 4 to 5, we said what happens? It speeds up, but in which direction? Downward. When is this object accelerating? When is this object accelerating according to this graph? The whole time. Right? Curved lines.
Oh, no, I put it away. Now make sure it's...
It's all in classroom, right?
What?
It's all in classroom.
These notes are not in classroom, but the calendar. All right, so if we encounter curved lines, we get a changing velocity. Okay? Tomorrow we'll get into time versus velocity graphs and analyze that a little bit more. Lab on Thursday.